Welcome to Math 201. This is our lesson on section 5.1, measuring distance traveled. Let's start by building some intuition. Imagine you and your favorite person are on a road trip. In version 1, you travel 60 miles per hour for 2 hours. How far do you travel? In general, remember that distance is rate times time. So we went 60 miles per hour times 2 hours. Our hours cancel, and that comes out to 120 miles. Okay, in version 2 of this road trip, your speed for 2 hours is every 2 hours is recorded in this table. And how far did you travel in those 2 hours? Okay, so let's see. We at time zero, we were traveling 30 miles per hour, and a half an hour later, we were traveling 40 miles per hour. So we can assume, or we're going to have to make some assumptions about our speed during this first half an hour. It could be 30, it could be 40, and it could be anything else, right? It could have gone way up. We could have hit 60 at some point. We don't know. We also could have stopped at some point to use buy a snack or use the bathroom, right? So we are going to have to make some assumptions. Okay. We don't know what happened in between time t equals zero and t equals a half, but we know that at t equals zero, we were going 30. Let's suppose we traveled 30 miles per hour for that whole half an hour. So our distance traveled for that first half an hour is rate is 30 and time is a half an hour. Okay. And then over my second half an hour from t equals a half to t equals 1, we start at 40 miles per hour and we finish at 60 miles per hour. We are going to have to make an assumption or a guess about what our speed was in between. I want to use one speed for the whole half an hour so that I can use distance equals rate times time. I'm going to use my 40 miles per hour. Okay, so for the next half an hour, I traveled 40 miles per hour for half an hour. Okay, and then from time t equals 1 to t equals 1.5, we're going to assume we traveled 60 miles per hour for that whole half an hour. Even though I could have done lots of other speeds in between there, we don't know. So we can only use the data that we have. So 60 miles per hour for another half an hour. And then from 1.5 to 2, we started at 60 and we finished at 55. We have no idea what happened in between, but I am going to make an assumption that I traveled 60 miles per hour for that whole half an hour. So another 60 miles per hour for half an hour. And then I can calculate these. So I have 15 plus 20 plus 30 plus 30, which is 95 miles. In version 3 of the story, our velocity is given by the graph. So how far did we travel? So I now actually know my speed at every moment um, of the trip. So time t equals 0 to t equals 2. I know what speed I was going at every moment, right? Instead of just knowing at time t equals 0 and t equals a half, I know my speed at every moment. Okay. So if I was going 30 for this entire first half an hour, or let's say this whole first hour, if I was going 30 miles per hour, I would multiply 30 miles per hour, right? 30 miles per hour times 1 hour. This would be 30 miles. And if I was going 60 miles per hour, 60 miles per hour for this whole hour, I would do 60 times 1, 1 by 60. 1 hour times 60 miles per hour, that would give me 60 miles. Okay, so, but instead of assuming I went 30 the whole time or I went 60 the whole time, I know how fast I went the whole time. And if I had gone 30, 1 times 30 is the area underneath that curve. It's the area of that rectangle. And if I went 60, 1 times 60 is the area underneath the height of 60. It's the area of that rectangle. So the area underneath the curve tells me distance traveled. So area under the curve equals distance traveled. Okay, so the area underneath this first linear portion, well, this rectangle is 1 by 30, so this is 30. And then I have this triangle that is 1 by 30, but it's a triangle, so you have to do 1/2 times 1 times 30, so that's 15. And then I have a rectangle here, which is 1/2 by 60, so that's another 30. And then my last region, my last half an hour, can be broken into a rectangle and a triangle. So the rectangle has a base of 1/2 and a height of 55. So 1/2 times 55 is 27.5. And then this last little triangle here, that is 1/2 times the base, which is 1/2 times the height, which is 5, because this is a height of 55, this is a height of 60, so this is a height of 5. Okay, and that equals 1/4 of 5 is 1 1/4. Okay, so my total distance traveled is going to be 15 plus 30 plus 30 plus 27.5 plus 1.25, and that comes out to 103.75 miles. Okay, we've reached our first activity for this lesson. I would like you to pause the video, work through this activity called road trip, and when you're ready to go over it, come back to the video and press play. A few of her friends took a road trip to upstate New York a few years ago and kept data on the trip. On the first day, the velocity of the car throughout the day was given by the following graph. Okay, how many miles did the group travel between 11 a.m. and 1 p.m.? And how does that distance relate to the graph? So time is measured in hours after 10 a.m. So t equals 0 is 10 a.m. And here's 6. So it looks like each tick mark on my axis is 1 hour. So this would be 1, 2, 3, 4, 5, 6. Yeah. So if this is 10, then this is 11, the next tick mark. So that's 11 a.m. And 1 p.m. would be right here. So we're looking at this time interval from 11 a.m. to 1 p.m., which is time t equals 1 to t equals 3. And how far did we travel? Well, that depends on how fast we were going on that time interval. And we were going a constant speed of 70 miles per hour. Sorry, 60 miles per hour. So here's our area under the curve. Okay, so this is 2. The height here is 60 miles per hour. So my distance traveled, oh, sorry, it's 65. Sorry, so if this is 0 and this is 70, we have 1, 2, 3, 4, 5, 6, 7 steps. So each of these is 10 miles per hour. So this is 10, 20, 30, 40, 50, 60. Yeah, okay, 60 miles per hour was correct. All right, so my distance is 2 hours times 60 miles per hour. And then you can see that the hours cancels. And what I'm left with is just miles, 2 times 60 miles, so 120 miles. Okay, and how does that relate to the graph? It's the area under the curve. It's the area of the shaded rectangle. Okay, how could you compute the distance traveled between 10 a.m. and 2 p.m.? So here's 10 a.m., 11, 12, 1, here's 2 p.m. So I want to find the area, the entire area under this curve. I already know that this middle section is 120. So this rectangular part, it's easy to find the area of. That was 120 miles. And then this little triangle here, it's got a base of 1 and a height of 60. So we're going to do, we've already got the 120. And then my triangle is 1/2 times base times height. And then I have a second triangle over here that's also 1/2 times a base of 1 times a height of 60. And that comes out to 120 plus 30, which is 180 miles. And number 3, compute the total distance traveled on the first day of driving. So that is for the entire graph, 12 hours of driving. I already know the distance I traveled in the first 4 hours. That was 180 miles. Okay, and then it looks like from t equals 4 to t equals 6, my velocity is 0, which means we took a break. Maybe we stopped for lunch. And so now I just need to figure out the area under this last part from t equals 6 to t equals 12. So I'm going to break it into shapes that are easier to find the area of. I've got this triangle and then a rectangle. Okay, and then the next part I can break into a rectangle and a triangle, and then a rectangle and then another triangle. Okay, so this triangle, it's got a base of 1 and a height of 50. So this is 1/2 times 1 times 50. That's this triangle here. Okay, and then we have the rectangle, which would be a base of 2 and a height of 50. So that's 2 hours at 50 miles per hour. That's 100 miles. Okay, and then this little triangle here, that is a base of 1 and a height of 20. So that's 1/2 times 1 times 20. And then the rectangle underneath, that is a base of 1, height of 30. So that's 30. So that's 40 miles for this interval of time from t equals 9 to t equals 10. 30 plus 40. And then from t equals 10 to t equals 11, we have a base of 1, that is 1 hour of driving at 30 miles per hour. So this is also 30. And then the last triangle, we have half an hour of driving, 30 miles per hour, but it's a triangle. So it's 1/2 1 times 30, which is 15. So this comes out to 390 miles. All right, they've given us an updated graph where the lines are now curvier. They're not just straight lines. And we want to find a good underestimate for the total distance traveled on the first day and explain your method. All right, so the exact area under this curve tells us how far we traveled exactly, but I want an underestimate. So I'm going to use shapes that are easy to find the area of, but I'm going to make sure that I don't count any area above the curve. So I want to have an underestimate for distance traveled, so I need an underestimate for area under the curve. So I'm going to use this rectangle for this whole first region. Okay, it's definitely an underestimate, okay, because there's a lot of area in that region that I'm not counting. Okay, so this pink rectangle is going to be an underestimate for the area under this first hump of my curve. Okay, so this is 2 by 60. This is 120. Okay, and then the second hump of my curve, I'm again going to use rectangles. And I'm going to use more than one rectangle this time. I could just use one rectangle, but it would be a vast underestimate. So maybe I'll do this rectangle and then also this rectangle. I'm still an underestimate, and this rectangle. So now I am counting most of the area that's under the curve, but it is still an underestimate because there are these bits that are not being counted by my rectangles. Okay, so this is 2 by 40, so 80. And then 1 by 30, which is 30. And this is 1 by 10, so 10. So 120 plus 80 plus 30 plus 10 would be 240 miles. Using the same updated graph, I want to find an overestimate for the total distance traveled on the first day. So I want to use rectangles again because they're easy to find the area of, and I'm going to overestimate the distance traveled by overestimating the area under the curve. So I'm going to count some area that that's not actually under the curve. All right, so I'm going to make a rectangle over this first hump. So you can see that that pink rectangle is more area than the area under the curve. I am counting some chunks here that aren't actually under the curve. There's too much area. That's making this an overestimate. So this pink rectangle is 1, 2, 3, it's 4 by 65, um, which is 260. And then this region over here, I'm going to use rectangles to overestimate it again. So I'm going to go to the very highest point on the graph and I'm going to do a rectangle, um, pretty wide rectangle to overestimate this area. So you can see that pink rectangle is more area than is under the curve. There's a bunch over here and a bunch here that I'm counting as part of the area of the rectangle that is not under the curve. And it's much more than these two little chunks that I ignored before. So this is much bigger and this is much bigger than these two little chunks. So I'm not gonna draw a rectangle here. I'm just gonna say this more than covers it. And this is 1, 2, 3, 4 units across and 10, 20, 30, 40, 50 units up. So this is 4 by 50, which is 200. Okay, and then I'm going to do two more rectangles on this last bit. I could just do one, but I'm going to do two. Um, so I've got an overestimate here and an overestimate here. And this rectangle is 1 by 30, so that's 30. And this last rectangle looks like it is 1 by maybe 13, so 13. So my overestimate is going to be 260 plus 200 plus 30 plus 13, which is about 505 miles. Okay, so our conclusion from class so far. The area under a positive velocity curve gives total distance traveled. Our next question is, what does negative velocity mean? Okay. Negative velocity means our speed, velocity is speed, but we are moving backwards, right? So that usually is left or down. We usually define the right to the moving to the right as the positive direction and moving up is the positive direction. So moving backwards would be moving left or moving down, and you would have negative velocity. Okay, we're going to talk about definite integrals. Definition: for a continuous function f of t on the interval a to b, the definite integral between A and B, denoted with this elongated S with an A and a B at the bottom and the top of f of t dt is the sum of the area between f of t and the t-axis with area above the t-axis counted positively and below the t-axis counted negatively. Note that if velocity is both positive and negative, the integral from a to b of f of t dt gives change in position or displacement from t equals a to t equals b. If v of t is given in the graph below, explain in words the meaning of each expression. So I've given some numbers in the graph here. We're telling you that the area between the curve and the x-axis from 0 to 15 is 30. And then the area between the curve and the x-axis from 15 to 20 is 7. So the integral from 0 to 20 of v of t dt, that's the area, the sum of the areas under the curves, with area above the x-axis counted as positive and below the x-axis counted as negative. So this is going to be 30 plus negative 7, which is 23. And what that calculates is displacement or change in position from t equals 0 to t equals 20. And then the integral from 0 to 20 of the absolute value of v of t dt, that's where we're going to make both of these areas positive, right? Because if we don't care what direction we're traveling, then we're going to consider all movement in the positive direction. Okay, so this is going to be 30 plus 7, which is 37. And this gives total distance traveled, where we don't care if we were moving left or moving right. We walked or drove a total of 37 miles or feet or whatever. Whereas up here, we did care what direction we were going. We went 30 feet to the right and then 7 feet back to the left. So we finished 23 feet from where we started in the positive direction. Okay. Here we went 30 feet to the right. We still went 7 feet to the left, but we don't care that we were going right and we were going left. We moved 30 feet, we moved 7 feet, so we moved a total of 37 feet. Now we're going to talk about approximating definite integrals. That is approximating area under a curve. We've been doing this all class by using rectangles and triangles, but we're just going to systematize it now. So here's a velocity graph, f of t, and I want to approximate the integral from a to b of f of t dt. That is, approximate the area under the curve. And first, I'm going to do that with a left-hand sum with 5 subdivisions. Okay, so first I'm going to label, this is going to be A, and we'll put B like right here, from A to B. And I want to break that into 5 equal parts. So that would be 1, 2, 3, 4. Sorry, I'm going to put B right here. B. Okay, so I broke that into 5 equal parts. And I want to use rectangles to estimate the area under the curve. And these are going to be the bases of my rectangles. So this is going to be a rectangle. I'm going to build on top of this base. Okay. And they said to use left hand sum. So that means I'm going to use the left end of the interval to find the height, to determine the height of the rectangle. I'm going to go to the left end of the interval. I'm going to go up to the curve, and that's going to determine the height of my rectangle. Okay, so I go up to the curve, up till I hit the curve. That's the height of my rectangle that I'm going to build over this first interval. Okay, and then for this second interval, I'm going to do the same thing. Here's my interval. I'm going to build a rectangle on top of it. To determine the height of that rectangle, because I'm using a left-hand sum, I'm going to go to the left endpoint. I'm going to go up to the curve. When I hit the curve, that's going to be the height of my rectangle. Okay, hit my curve. So that's going to be the height of the rectangle for that entire interval. Okay, and then I just keep repeating. So here's my third interval. To determine the height of the rectangle that I'm going to draw on top of that base, I'm going to go to the left endpoint of the interval. I'm going to go up until I hit the curve, and that's going to be the height of my rectangle. So here's where I hit the curve, and then I make my rectangle have that height. And then fourth interval, go to the left endpoint of the interval, go up till you hit the curve. That's going to determine the height of your rectangle on that interval. And then for my last interval, we repeat again. We go to the left endpoint, go up till you hit the curve, and that determines the height of your rectangle. So if I were to shade these rectangles in, they would give me an estimate of the area under the curve. Okay, another way that we can estimate the area under the curve is with right-hand sums. So again, I'm going to mark my A and my B. Oops. Okay, so here's my B, here's my A. I'm going to do 5 subdivisions again. So I take this whole interval A to B, I'm breaking it into 5 equal parts. And this time I'm going to use a right-hand sum. So the basic idea is the same. Each of these subdivisions is going to form the base of a rectangle. So I'm going to build a rectangle on top of this interval. So this interval is going to be the base of my rectangle, and I'm going to build a rectangle on top of it. The height of the rectangle is determined by the right-hand endpoint of that interval. So I go to the right-hand endpoint of that interval, I go up until I hit the curve, and that tells me the height of the rectangle over that interval. So just go up till we hit the curve. That is the height of my rectangle over that interval. And then we just keep doing that on each interval. So next interval, I go to the right end point, I go up to the curve. When I hit it, I make that the height of my rectangle. So this is just another way that we could estimate the area under the curve. We can use a right-hand sum. So for both of these, the base of each rectangle is always the same. We call this delta t. It's a small change in t. So we call all of those delta t's. Because we took the interval from A to B, and we broke it into 5 equal parts. So they're all the same. And the way that we calculate delta t is we take the length from A to B, which we do by subtracting B minus A, and we divided it into 5 equal pieces. So now we're going to define what a left-hand sum is with n equal subdivisions. We're going to define a left sum and a right sum with n equal subdivisions. So it's an estimate for the area for the definite integral, the area under a curve from A to B. And if we're going to break it into um, n subdivisions, then my delta t is going to be b minus a over n. Okay, but in general, we're going to be adding up a bunch of rectangles. So we're going to have delta t. I'm going to do pink because this is like, I'm looking at the pink one as my example to write out a general formula here. So each rectangle is delta t times the height of the rectangle at the left endpoint. So for this first rectangle, the left endpoint is A. So this is delta t times f of A. Okay, and then my next rectangle, the base is delta t again, and the height of this rectangle is the height of the rectangle at the left endpoint, the height of the function at the left endpoint. And this point right here, we could measure by doing A plus delta t. And then my next rectangle has a base of delta t and a height is the height of the function at the left endpoint, which would be right here. And the way I figure out this x value is I say, okay, well, it's a plus delta t plus delta t. So a plus 2 delta t's. Okay, and we keep doing this until we get to the last rectangle, and it has a base of delta t, and it has a height, the left endpoint of the last interval. So not b, but 1 delta t before you get to b. So that would be b minus delta t. Function value at b minus delta t. So now I'm going to do a similar definition for a right sum with n subdivisions. And I'm going to look at my green picture here because this was my example of a right-hand sum. So if I had n rectangles instead of 5 rectangles, I would calculate it by adding up rectangles again. This first rectangle has a base of delta t, and then the height is the height of the function at the right endpoint. So this is the right endpoint of the first rectangle. It's a plus delta t, and that's the function value at that x value. So this is delta t times f of a plus delta t. Okay, and then my second rectangle, it has a base of delta t, and then its height is determined by the height of the function at the right endpoint. So we go to the right endpoint of that interval, and that is located at a plus delta t plus delta t. So a plus 2 delta t, and we go up to the height of the function at that x value. So this is f of a plus 2 delta t. And then we keep doing that for all the rectangles until we get to the last rectangle, which has a base of delta t, and its height is the height of the function at the right endpoint. So the right endpoint of this interval is at b, so the height is f of b. And for both the left and right um, sums, my delta t is the length of the entire interval, which is b minus a, and we're going to divide it into n equal pieces. In our example, we divided it into 5 equal pieces, but here we're trying to define it for a general n. So I'm going to do the length of delta t is going to be b minus a, which is the full length, divided it into n equal pieces. And note, just as a way to check your work sometimes, we should say that the number of subdivisions we make, the n value, equals the number of terms in your sum. We've reached our second activity for lesson 5.1. Pause the video, take a few minutes, try these problems. When you're ready to go over them, come back and press play. Approximate the definite integral from 2 to 6 of f of x dx using a left-hand sum with two subdivisions. All right, so 2 and 6, those are my bounds. Those are x values. So I'm going to mark this on the graph, 2 to 6. Okay, and it says two subdivisions. So I'm going to take this entire interval from 2 to 6 and break it into two equal pieces. So just cut it in half. And now I have two subdivisions, 1, 2. And I want to use a left-hand sum. So a left-hand sum means that for each interval, we're going to build a rectangle, and the height of the rectangle is the height of the function at the left endpoint. So the left endpoint from 2 to 4 is at 2, and the height of the function is 0. So this rectangle is just a flat line, has no height. Okay. And then I'm going to look at my second interval from 4 to 6, and I'm going to build a rectangle on top of this base, and the height is going to be the height of the function at 4, the left endpoint of that interval. So at 4, I'm going to go up until I hit the function, and then I'm going to make that the height of my rectangle. So I'm going to add these two rectangles together. The first rectangle had a base of 2 and a height of 0. And the second rectangle has a base of 2 and a height of 2. So this is 4. So just to write this out a little bit more formally, I would say the integral from 2 to 6 of f of x dx. So that is the area under the curve from 2 to 6, all of this area. We are approximating it using a left-hand sum with two subdivisions. And that came out to 2 times 0 plus 2 times 2 to give us 4. Now I'm going to approximate the definite integral from 2 to 6 of f of x dx. Again, left-hand sum, but this time I'm going to use 4 subdivisions. So I'm going to mark 2 to 6 again. So that's the length of my entire interval from 2 to 6. So I'm going to mark the 2, I'm going to mark the 6, and I want to break it into 4 subdivisions. So I'm going to break it into 4 equal pieces. And on each of those intervals, I'm going to build a rectangle. The height of the rectangle is the height of the function at the left endpoint. So from 2 to 3, the height of the function at 2 is 0. So that's just a flat rectangle. Then from 3 to 4, I'm going to build a rectangle. The height is going to be the height of the function at 3. So I'm going to start at 3. I'm going to go up to the graph till I hit it, and I'm going to build a rectangle that has that height. And then I keep doing that over each interval, and I get the area of each rectangle. This one is 1, 2, and looks like about 2.5. So I would say the integral from 2 to 6 of f of x dx. We are approximating using a left-hand sum with 4 subdivisions. And I can calculate that where this first rectangle, it has a base of 1 and a height of 0. Second rectangle has a base of 1 and a height of 1. Third rectangle has a base of 1 and a height of 2. And the fourth rectangle has a base of 1 and a height of 2.5. And that comes out to 5.5. We're going to approximate the same integral from 2 to 6 of f of x dx, this time using a right-hand sum and 4 subdivisions. Right-hand sum, 4 subdivisions. So I'm going to mark 2 and I'm going to mark 6. I'm going to break it into 4 equal parts. I'm going to build a rectangle over each of those intervals. This time I'm going to determine the height of the rectangle using the right endpoint of the interval. So the interval from 2 to 3, we use the right endpoint at 3 to go up to the graph and build a rectangle at that height. And then I do that on each interval. Go to the right endpoint, go up till you hit the graph, and then you draw a rectangle at that height. And then I'm going to find the area of each of these rectangles and add them up. And that will give me an approximation for the integral from 2 to 6 of f of x dx. We're going to approximate this with a right-hand sum with 4 subdivisions. And that's just the sum of the areas of these rectangles. So this first rectangle is base of 1, height of 1. Second rectangle is base of 1, height of 2. Third rectangle is a base of 1, height of 2.5. And then the third rectangle is a base of 1, height of 3. And that comes out to 8.5. Now we're going to approximate the definite integral from -3 to 2 of f of x dx using a left-hand sum with 5 subdivisions. Okay, so -3 and 2 is the entire interval. I'm trying to estimate the area under the curve between x equals -3 and x equals 2. I'm going to mark those x values, -3 and 2. And then I want to break it into 5 subdivisions. Take this whole interval, break it up into 5 equal pieces, 5 subdivisions. So 1, 2, 3, 4, 5. That's 1, 2, 3, 4, 5 subdivisions of this entire interval. And I want to use a left-hand sum. So for each of those subdivisions, I'm going to build a rectangle. The height of the rectangle is going to be the height of the function at the left endpoint. So I go to the left endpoint up till you hit the graph, draw a rectangle. So I've represented this estimate on the graph by drawing the rectangles. Now I'm just going to calculate my estimate by finding the area of those rectangles and adding them up. So I'm looking at the integral from -3 to 2 of f of x dx. I'm going to approximate that with a left-hand sum with 5 subdivisions. And that is just the sum of the rectangles, the sum of the areas of the rectangles I drew. So this first rectangle, it has a base of 1 and a height of 1. So this is 1 times 1. Second rectangle has a base of 1 and a height of 2.5. Okay, my third rectangle has a base of 1 and a height of 4. My fourth rectangle has a base of 1 and a height of maybe 2.6. So it looks like maybe it's a tiny bit higher than this one over here. And then my last rectangle has a base of 1 and a height of maybe 1.4. And that comes out to 11.5. And number 4, now I'm going to approximate the same integral from -3 to 2 of f of x dx with a right-hand sum with 5 subdivisions. So I'm going to mark -3 and 2, break it into 5 equal subdivisions. I'm going to build a rectangle over each one, but this time the height of the rectangle is going to be the height of the function at the right-hand endpoint. So we go to the right endpoint for this first interval, go up to the graph, build a rectangle at that height. We do that for each interval. So this last interval, the height of the function is at 0, so it doesn't have any height. So my integral from -3 to 2 of f of x dx, this time we're approximating it with a right-hand sum, 5 subdivisions, and I'm just going to add up the areas of these rectangles. First rectangle, base of 1, height of 2.5. Second rectangle, base of 1, height of 4. Third rectangle, base of 1, height of 2.6. Fourth rectangle, base of 1, height of 1.4. And the last rectangle has a base of 1, height of 0. And that comes out to 10.5. Number 5, I want to compute the exact values for the two integrals that we've just been estimating. The integral from 2 to 6 of f of x dx and the integral from -3 to 2 of f of x dx. I can do that because the area under the curve, the integral is the area under the curve, and these two integrals are represented by just straight lines. The functions are just straight lines, so I can find those areas. So the integral from 2 to 6 of f of x dx, that is the area under the curve between the curve and the x-axis. So I'm just going to break this into pieces that I can calculate the area of. I've got this rectangle here, which has a base of 2 and a height of 2. So 1/2 times 2 times 2. And then I have this piece over here, which I can break into a rectangle with a triangle on top. So this is 2. This square is 2 by 2, so that's a 4. And then this triangle on top is 2 by 1. So it'd be 1/2 times 2 times 1, which is 1. And that comes out to 7. All right, and then the integral from -3 to 2, that is from -3 to 2, that is this area. All of this area, and it's all just straight lines. So I'm just going to break it into shapes that I know formulas for to find the area. All right, I'm going to start with the interval from -3 to 1. So I'm going to draw that there, and I can break that into a rectangle with a triangle on top. So the rectangle on the bottom is a base of 2, height of 1. So that's got an area of 2. And then the triangle above it, it's got a base of 2, height of 3, because it goes from 1 to 4. So this distance is 3. So this is 1/2 times 2 times 3, which is 3. And then what's left here, over here, is just one big triangle. It has a base of 1, 2, 3, base of 3, height of 4. So 1/2 times 3 times 4 would give me 6. So this is 3 plus 2 plus 6, which is 11.